Good evening, students. I'm going to start the class today. Okay, so let's start our work. Okay, so today we are going to uh, continue with the upthrust force. Last week we continued our lesson and finished that YouTube practical, then the Pascal's principle, then special properties of pressure, all of these things. Now we are up to upthrust force in hydrostatics. Okay, shall we write the topic now? It's time to start. Okay, so write the topic, upthrust force. The next subtopic, upthrust force. The next subtopic, upthrust force. Upthrust force. Okay. Okay. Now, what is upthrust force? What is upthrust force? First, listen about this thing. This is a liquid container. This is a liquid container. This is a liquid container. Take a rubber ball. Take a rubber ball and immerse it in the liquid. Take a rubber ball and immerse it in the liquid. Place it inside the liquid from your hand. Try to keep it inside the liquid. What will happen? You take a rubber ball and you dip it inside the liquid and you try to keep it inside. You will feel there's a force that's acting on the ball, trying to push the ball upward. This force, you can feel it. It is the upthrust force. We are going to understand how this upthrust force creates. That's what our first topic today. Okay, write a small sentence. When an object is immersed in water, when an object is immersed in a liquid, upthrust force, when an object is immersed in a liquid, upthrust force, push it upward. Upthrust force, push it upward. Okay, upthrust force, push the object upward. When an object is immersed in a liquid, upthrust force, push it upward. Okay, so now see what I'm going to do. This is a liquid container. In this liquid, I'll enter an object like this. So inside the liquid container, an object like this is immersed. Okay. I'll draw the liquid from blue color this time. I'll draw the liquid from blue color. I'll draw the liquid from blue color, and then this is the thing. Okay. Inside the liquid container, the liquid having a density rho. The liquid is having a density rho. Inside this liquid, now there's a object placed. This is a height h1. This is a height h1. Okay. So at this level, at this is the height h1. So at this level, pressure is equal to atmospheric pressure P5, plus H1 rho G is the pressure in this place. Children, what am I doing at the moment? Upthrust force. Upthrust force is the force when you consider this example, when you place a ball inside the liquid and you try to keep it inside a rubber ball inside the liquid, you will feel your hands, you will feel that it tries to move up. Something is pushing the ball upward. It is the upthrust force acting on an object which is immersed inside the liquid. The liquid creates a force on the object upward, upthrust force. We are going to see how this upthrust force is created. Okay, now, so this is a liquid container. Here inside this liquid container, there's a rectangular shaped object at a depth h1. At a depth h1, atmospheric pressure P5, pressure is equal to pressure from the atmosphere P5 plus h1 rho g, pressure at this level. If the surface area of the if the surface area is A, you have to understand the pressure is equal to force over area. So pressure into area is the force. Pressure into area is the force. Pressure into area is the force. So what will happen? So the force acting on this place, let's say F1, force acting on this place, F1, pressure P5 plus H1 rho G, and when you multiply the pressure by the area, you will get the force acting on this place. So the force F1 value will be equal to, force is equal to pressure P5 plus H1 rho G times A. Okay, let's start. We are going to see how the upthrust force is created. Okay, let's start from here. Draw the diagram. Inside the liquid container, draw a rectangular shaped object, and in that object, area is A, pressure P5 plus H1 rho G at this level. When you multiply the pressure on that level by the area that the pressure is acting, you will get the force created as per the last week theory. So in this rectangular object, a force F1 is acting downward, and we have this value. Okay, finish up to that point. Okay, you can finish up to this point. Today the lesson is about the upthrust force. Continue and give me a value for the pressure at this level. Now as the next thing, give me a value for the pressure at this level. Give me a value for the pressure at this level. Okay, so this is the briefing. Today we are going to start to learn about the upthrust force. When you place a object inside the liquid from your hand, you will feel that the liquid is pushing the object upward. You will feel that force. It's known as the upthrust force. It's very important in hydrostatics because when you immerse the object inside the liquid, you feel this force, the upthrust force. We are going to know how the upthrust force is created. Okay, see, to take a proof about the upthrust force, to take an equation about the upthrust force, here I have shown you some special thing. This is a liquid container. Inside this liquid container, I have placed a rectangular shaped object. At a level H1, the pressure value due to the liquid at the atmosphere is pressing the surface by P5 atmospheric pressure plus H1 rho g. P5 plus H1 rho g is the pressure in this level. When the pressure is multiplied by the area, you get the force created. So the force created on the rectangular object downward F1 is related to pressure P5 plus H1 rho g, pressure in this level multiplied by the area. Then you will get the force acting on the object downward. This F1. Okay. Now take this thing. From here, the depth up to the lower level of the object, from here, the depth up to the lower level of the object is equal to P5 plus H2 rho g. From last week knowledge, atmospheric pressure plus H2 rho g will be the liquid pressure in this level. And last week I told you a very special theory. Can you remember? When you take a balloon filled with a liquid, and when you make a small hole on it, on this place, what happens? The liquid will come out in this direction. What do you mean by that? Before creating the hole, the liquid was feeling a pressure, and as soon as you opened it, the liquid jumped outside. Due to that pressure, it was feeling. What do you mean by that? Pressure acts upward also. Last week we discussed. Pressure is acting upwards also. So, to write the pressure value here, atmospheric pressure P5 plus H2 rho g is the pressure value as it is the lower level of the object. This is the place, and pressure is acting upward also. So the force here, F2, it's acting upward also, F2. So the force here, F2 is equal to pressure multiplied by the area, P5 plus H2 rho g multiplied by the area. P5 plus H2 rho g multiplied by the area. So you place the rectangular object inside water. On the top level of it, you write the pressure, and you multiply it by the area of the object. You get the force that the pressure is pulling the object downward. You write the pressure at the lower level of the object, P5 plus H2 rho g, and you multiply it by the area. Then you will get the related force. You know from this example, pressure can act upward also. If the relevant surface is placed on the top of that level, pressure can create a force on that side also. So pressure will create a force on this side, F2. Okay. So now what has happened to the object? What is the resultant force acting on the object? the resultant force. Now you can write with me the resultant force. The resultant force acting on the object. The resultant force acting on the object from the liquid pressure. From the liquid pressure. What is the resultant force acting on the object from the liquid pressure? Due to the liquid pressure on the top side, F1. Due to the liquid pressure from the bottom side, it's F2. So what is the resultant force? F2 is acting upward, F1 is downward. F2 minus F1. This is known as the upthrust force. This is known as the upthrust force. This is known as the upthrust force. Okay? That is the thing. When you immerse the object inside the liquid, its top level feel less pressure, P5 plus H1 rho G, smaller value. Its bottom level will feel high pressure, P5 plus H2 rho G, the bottom level. As pressure is acting in any kind of a direction on the top level, as the surface area is like this, pressure will create the force downward. As the pressure has the property that it can act upward. If the relevant surface is located in a position like this, when the pressure is concerned here, it can create a force on this side too. So for the other object, F2 is acting upward. As the F2 is the higher value, due to high H value, F2 is large. So what is the resultant force? F2 minus F1. Due to the pressure difference, the resultant force acting on the object is F2 minus F1. It is the upthrust. It is the upthrust. F2 minus F1. F2 P5 plus H2 rho G times A minus F1 P5 plus H1 rho G times A. Let's simplify. You can do it with me. You can do it with me. So what is upthrust? P5A H2A rho G minus P5A minus H1A rho G. P5A will cancel out. Upthrust is equal to H2 minus H1A rho G. Upthrust is equal to H2 minus H1A rho G. Finish up to that point. When an object is immersed inside a liquid, its top level will feel less force due to the less pressure value, due to the less H value. Its bottom surface will feel high pressure due to high H value, high depth, and force will acting, it will face a force acting upward with a high value, F2. So the object will feel a resultant force of F2 minus F1. The resultant force felt by the object upward due to the pressure difference is the upthrust. H2 minus H1 A rho G. What is H2 minus H1? H2 is the full depth. H1 is the depth up to the higher initial position of the object. So H2 minus H1 is the height of the object. You can mark them. H2 minus H1 is the height of the object. H2 minus H1 is the height of the object. You multiply it by the surface area A. It is the volume. It is the volume. Remember this volume. You can see that it is the H2 minus H1 multiplied by the surface area. Height multiplied by the area, volume of the object. But remember, in the actual case, this is the volume inside the liquid. Volume of the object that is inside the liquid. Here, as the full object is inside the liquid, one might say this is the object, this is H2 minus H1. A is the volume of the object. Yes, but in the fair case, when you take it fairly, what is the case? This H2 minus H1 into A, it's the volume of the object, true, but it's the volume of the object that is inside the liquid. So, upthrust is equal to volume density of the liquid G. When you write the pressure, you use the density of the liquid. When you write the pressure, you use the density of the liquid. Density of the liquid G and the volume. What is this V? V is equal to volume of the object inside the liquid. Feel it, huh? Volume of the object inside the liquid. Volume of the object inside the liquid. Volume of the object inside the liquid. Okay, so take a brief idea now. When you immerse the object inside the liquid, you can feel the upthrust force acting on it upward, and this upthrust force is acting on the object due to the pressure difference that the object feels, and the resultant force F2 minus F1 created from the pressure difference is known as the upthrust, and it's equal to V rho liquid G, where V is the volume of the object which is inside the liquid. Okay, so this is the case. Now we proved this equation. Using Newtonian mechanics. Newton was born in 16th century, and force and the pressure, these things were theories related to him, and these are the theories in 16th century. But have you heard about the scientist called Archimedes? He lived 2000 years back, but still, have you heard that story? He jumped to the bathtub. King at that time, king asked him to check whether the crown is made from original gold. For that, he had to do an experiment. While he was thinking about the experiment to find whether the gold is pure in the crown, he jumped to the bathtub, and when he jumps to the bathtub, water went away, water was displaced, and he got the idea and he shouted Eureka, Eureka, and ran without clothes. Have you heard this story? I think yes. At that case, so in your O-levels, by that story, you are taught about the upthrust force and the Archimedes principle. Now, without using a single part of the Archimedes principle, using the pressure difference from the Newtonian mechanics, now I have proved the upthrust force. So remember, this is the upthrust force, and this is how it is created from the Newton mechanics. But in our syllabus, we have to pay the attention for that one also, the Archimedes principle. How the upthrust force is taken using the Archimedes principle. That is the next thing. We'll use the Archimedes principle, and we have to finish up with the same equation. That's the case. Okay, now write down Archimedes principle to prove the upthrust force. 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 The next thing, Archimedes principle to prove the upthrust force. Okay, first we will write the Archimedes principle, then we will show that through the Archimedes principle we can get the same equation. Okay, write down Write down. When an object is immersed in a liquid, when an object is immersed in a liquid, the principle. When an object is immersed in a liquid, when an object is immersed in a liquid, within brackets, fully or partially, within brackets, fully or partially. You can place the object fully inside the liquid, or you can place the object partially inside the liquid. Okay, when an object is immersed in a liquid, within brackets, fully or partially, it will face the upthrust force. It will face the upthrust force. It will face the upthrust force that is equal to the it will face upthrust force that is equal to the volume of liquid, that is equal to the weight of the volume of liquid, that is equal to the weight of volume of the liquid, that is equal to the weight of volume of the liquid which was displaced Okay, read it once. When an object is immersed inside water, when an object is immersed inside a liquid, fully or partially, it will feel upthrust force. It will feel upthrust force equal to the weight of the liquid, that it displaced, Here, I'll take a container like this. This container is special. It has a drain. It has a drain like this. And I will fill water. I will fill the liquid to the top. I will fill the liquid to the top. Okay. Now there's a liquid container which is filled by the liquid to the topmost point. And there's an object placed here. And now I'm going to immerse the object inside the liquid. Okay, let's see. Now, the liquid is fully filled to the container. You have this drain, and I will place another container. To handle the liquid that is coming out. Why? Now here, when the object is placed on the liquid, what happens? Liquid is okay. Still the liquid is present in the areas that I am drawing. But consider this border. And hypothetically, this is the border. In the first image, you will see the border that the object will take after it is immersed. Okay, so this is what's happening here. here the full liquid is present, but when you fill the object inside, the liquid parts in this area, they will move out. Liquid parts in this area will move out, and you can collect it from here. So this is the volume displaced. When an object is fully or partially immersed inside a liquid, a certain volume of liquid will be displaced. While when the object comes to live here, take this hypothetical border. The liquid molecules which are inside this hypothetical border, now that space is taken by the object. So the liquid molecules which are occupying that space, now they don't have a place to live. They have to move out. So the volume displaced is here. The volume displaced is equal to volume of the liquid, volume of the object inside the liquid, isn't it? Inside the liquid. So Archimedes says upthrust is equal to, Archimedes says, read what I have given you. Archimedes says upthrust is equal to, Archimedes says upthrust is equal to the weight of the liquid displaced. I'll brief it again. From the earlier method, from Newtonian mechanics, we proved what upthrust is and we took the value equation. But 1600 years before, Archimedes told it in a different way but the same equation. He suggests that the upthrust force acting on the object is equal to the weight of the liquid that is being displaced when we immerse the object into the liquid. Here I have immersed the object into the liquid. When I immerse the object into the liquid, previously these places were occupied by liquid molecules, but when the object came to that place, liquid molecules on that place had to move out. So the displaced volume is the same volume that the object is occupying now. Okay, so one can say volume displaced is equal to volume of the object inside the liquid. It's clear. Now Archimedes says upthrust force is equal to weight of the liquid displaced. The weight of the liquid displaced is equal to upthrust force according to him. Weight of the liquid displaced. What is the volume of the liquid displaced? Volume of the liquid that was displaced is equal to the volume of the object that is immersed inside. So I can rewrite it. Weight of the liquid having the same volume, weight of the liquid displaced, I can rewrite it, weight of the liquid having the same volume which the object is immersed. Okay, so what is the method to write the weight of a liquid? Mass of a liquid can be written as density into volume. Mass of a liquid can be written by density into volume. So weight of a liquid can be written by density, volume into acceleration of gravity. Mass of a liquid density into volume. Weight of a liquid, density, volume into acceleration of gravity. So Archimedes suggests upthrust force acting on the object. Upthrust force acting on the object is equal to the weight of the liquid which was displaced. Weight of the liquid which was displaced. What is the volume of the liquid which was displaced? It's the same volume where the object is occupied now. Okay, so we can rewrite it. So we have to write the weight of the liquid having a volume is that equal to, we can write the weight of the liquid that's having a volume where that volume is equal to this volume, the volume that the object is immersed. Okay, so how to write the volume of a liquid? Density of the liquid, volume of the liquid, acceleration of gravity. Here, what is this volume of the liquid? It is the volume here. What is it? It is the volume here. The liquid came out when the object occupies that volume. So this volume is the occupied volume by the object inside the liquid. It's the same thing. It's the same thing. So upthrust is equal to V, volume of the object that is immersed inside the liquid, rho, density, G. Okay, now you can complete it again. You can rewrite it again. The same V. Volume of the object. That's inside the liquid. That's inside the liquid. Okay, while you are finishing up the note, I'll be briefing the situation. Today our topic is about the upthrust force. What is the upthrust force? When you immerse an object inside a liquid, you will feel that the liquid is pushing the object upward. It's the upthrust force. From the Newtonian mechanics, it's created due to the pressure difference in the top level and the bottom level. On the top level, pressure is less. On the bottom level, pressure is high. When you write that pressure and multiply it by the surface area, you will get the force created by the pressure. In the top, you have a less force. In the bottom, you have a higher force. As pressure is acting upwards also, that bottom force acting from the bottom is acting upward. So that is higher one, F2 minus smaller one, F1. So there's a resultant force acting upward. It's known as the upthrust, F2 minus F1. When you simplify it, you will get that the upthrust is equal to V rho G, where V is the volume of the object that is inside the liquid, rho, density of the liquid, G, acceleration of gravity. And these theories are from 16th century. But 1600 years ago, before Jesus Christ was born, there was a scientist called Archimedes. he gave the same theory in a different manner. That Eureka story, when he jumped to the bathtub, water was displaced outside. From there, he started the thinking pattern of this thing, and he finished with this equation. And this equation helped him to calculate the thing he needed to prove in front of the king. It's a long story. Okay. Now he says, when an object is immersed inside the water, it feels upthrust force, and that upthrust, he don't explain it by the pressure difference. That upthrust force acting upward on the object is equal to the weight of the liquid that is being displaced. So if we can calculate the weight of the liquid that was displaced due to the immersement of this object, upthrust force is calculated. So we'll apply a small technique. Continue this and listen. While writing this, you can listen. Take a container fully filled with the liquid. Immerse the object on it. When you immerse the object to a fully filled liquid container, a certain amount of liquid will be displaced. Collect it and think of a method to write the weight of that displaced liquid. What is the volume of the displaced liquid? Volume of the displaced liquid is equal to the volume of the object that is inside the liquid. When the object is placed, the previous areas which was occupied by the liquid molecules, a certain area is now occupied by the part of the object. That water molecules, liquid molecules which are on that space will be displaced, and that place is now occupied by the object. So consider this boundary. See the hypothetical boundary here. The liquid molecules in these areas are displaced now. Why? The object is occupying that area. Okay. So the weight of the liquid displaced is equal to upthrust. To calculate the weight of a liquid, you have to multiply density, volume, acceleration of gravity. U is equal to V rho G. And what is this V? Density of the liquid, the volume of the liquid displaced. What is the volume of the liquid displaced? It's equal to the volume of the object that is immersed inside the water. So upthrust is the same case now. You will get the same equation. Okay, from these both methods, you can take a proof to the upthrust. Okay, let's move to the questions. Question number 36. There's a error in the numbers. Okay, let's move in the way that you shows us. Question number 36. Question number 36. Then question number 37, 36, 37, 39, 45, 45, 46, 49. Okay. First, finish the set of questions here. 36, 37, 39, 45, 46, 49. Okay, question number 36. Now you know when a metal coin, when a coin it's made of metal, you immerse the metal inside the water container, metal will go down. Remember those things, huh? You can prove, but in your level, you can use it without any proof. Remember them, huh? When you have a high dense liquid, sorry, when you have a high dense object, when the object density is higher than the liquid density, object will move down through the liquid. And when the object density is lesser than the liquid density, it will float. It will float. Okay? And if an object which is having a less density, if you placed it inside the liquid, it can't wait inside, it has to come up, it will move up to float in the surface. So here, the object that you have entered to the liquid, object that you have placed inside the liquid is having a lesser density. Object that you have placed inside the liquid is having a lesser density. So it can't stay there. It ought to be floating on the surface. So it will try to come up. It will try to come up as it's having a lesser density. Less dense objects are being floating in the liquid. So it will try to come up to float. So there's a tension that is attached to the object. Without it will not allow it to move up. Why? The tension attracts the connected point towards the string itself. It is the direction here. Tension attracts the connected point towards the string itself. Tension attracts the connected point towards the string itself. So the direction is a downward direction. So the tension will keep the object in the middle area of the liquid. As the density is less, it needs to come up, but it will remain here due to the tension. And normally it has the weight also. Normally it has the weight also mg. Mg is also there. The tension and the weight both are present. And now you know when an object is inside the liquid, it has the upthrust. When an object is inside the liquid, it has the upthrust. You have the upthrust, tension force, downward, mg, downward. Okay, now it's in equilibrium. Object is in equilibrium, it's not moving. So force acting on it due to the liquid, the upthrust U will be balanced by the weight of the object, always downward, and the tension. String is attracting the connected point towards the string itself, that means downward. So this is how upthrust is managed by the weight and tension, the two downward forces. Okay, what is the upthrust? Volume inside the liquid, volume of the object that is inside the liquid, density of the liquid G is equal to mg plus T. What is the volume of the liquid? What is the volume of the object that is inside the liquid? It's same as the total volume, because the total volume of the object is inside the liquid. From the question you can finalize it. From the type of the question they have asked, you will understand it that the total volume is inside the liquid. So in the upthrust, we have to substitute the amount of the volume of the object that is inside the liquid. Here it's the total volume of the object. So for this thing, you can apply the total volume, density of the liquid G, mg plus T. What is the total volume of the object? What is the total volume of the object? 500 centimeter cubes. 500 centimeters centimeters. 500 centimeter 10 to the power minus 2 meters. Centimeter 10 to the power minus 2 meters. Centimeter 10 to the power minus 2 meters. So 500 into 10 to the power 6 meter cubes. 500 into 10 to the power minus 6 meter cubes. Why? 1 centimeter 10 to the power minus 2 meter. So total volume, that means the volume of the object that is inside the liquid. 500 into 10 to the power minus 6. Density of the liquid 10 to the power 3 water, G10 upthrust is managed by the weight and the tension. Weight and the tension. So we have to write the weight of the object and we can find the tension. Weight of the object mg, total volume multiplied by the density of the object will give the mass of the object. To write the weight of the object, you can write volume, the total volume multiplied by the object density. Total volume, it's also 500 into 10 to the power minus 6 multiplied by the object density will give the object mass. Object density is 800. Object density multiplied by the object volume, object mass multiplied by 10. Object weight 1, 2, 3, 4, 5. 4 newtons. So here mg is 4 plus t. 1, 2, 3, 5 is equal to 4 plus t. Tension is equal to a 1 Newton value. If the situation is this, tension is equal to a 1 Newton value. Tension is equal to a 1 Newton value. And then they ask what will happen if the string was cut. What will happen if the string was cut? Now the tension is not there. If the string is cut, no tension. Only the upthrust and the weight. Only the upthrust and the weight. So I'm applying F equals ma upward. Upthrust U minus mg. Because in F equals ma, F is the resultant force. F is the resultant force. So what is the resultant force? No tension. String is cut. Upthrust minus weight is the resultant force. Upwards, mass times acceleration. What is the upthrust? Volume inside the liquid, density of the liquid g. Volume inside the liquid is equal to the volume of the object here. Density of the liquid 10 to the power 3 g. 5. Answer is 5, you know that. What is the weight of the object? Volume of the object multiplied by the density of the object by 10. And you got the answer 4. 5 minus 4. If the weight is 4, mass is 0.4. A. 5 minus 4, 1 over 0.4 will be the acceleration. 2.5 meters per second. 2.5 meters per second. Okay. Continue your work. Now come to question number 37. Come to question number 37. Okay, continue with the question. Question number 37. Question number 37. An object of volume 200 centimeter cubes and density 400. This is the liquid container, and in the liquid container there's an object. Can you see? The density of the object is less. Remember that. Less, you can prove it, but you can remember, you have the freedom. The less dense objects, when they are immersed inside the liquid, rubber balls inside water, they try to move up. If you need to keep them inside the liquid, you have to tie them to the bottom with a string, and that string will create a tension downward, T, acting the connected point towards the string itself. And the rubber ball or whatever, it has the weight also. Two forces that are being acting downward will be managed by the upthrust and will be keeping the equilibrium. Okay, U is equal to mg plus T here. Upthrust, volume of the object inside the liquid, density of the liquid G, weight of the object, volume of the object, density of the object G plus T. Here the full object is inside the liquid. So to write the upthrust, you need the volume of the object inside the liquid. It's equal to the volume of the object here. Full one is inside the liquid. Plus T. Okay. So what is the volume? 200 into 10 to the power minus 6. Liquid density 10 to the power 3 G10. Volume of the object, it's also 200 into 10 to the power 6, same, full volume inside, but the density differs, it's just 400 G plus T. What will happen? 1, 2, 3, 2 is equal to 1, 2, 3, 4, 5, 0.2 plus T. T is equal to 1.8 newtons. If this kind of object is needed to be kept inside the liquid without moving upward, the tension of the string that it should be tied to the bottom is equal to 1.8 newtons. Is equal to 1.8 newtons. Then what else? The second question. The second part. If the string is suddenly cut, find the acceleration with which the object moves upward through the water. Let's apply F equals ma upwards. Let's apply F equals ma upward. F is the resultant force. F is the resultant force. What is it? Now the string is no longer there. Now the string is no longer there. String is cut. So the resultant force, upthrust minus mg. Upthrust minus mg, ma. Upthrust is equal to 2. From the calculation, you know that upthrust is equal to 2 minus mg. Weight is equal to 0.2. From the calculation, you know that it was 0.2. If the weight is 0.2, mass 0.02. 0.02. If the weight is 0.2, mass 0.02 A. So 1.8 divided by 0.02 will be the acceleration. Will be the acceleration. 1.8. 1.8 divided by 0.02. Beta. The tension, the upthrust, it's equal to 2. Here it's 0.8. Here it's 0.8. Here the weight is equal to 0.8. So you have 0.8 here. So the 2 minus 0.8, 1.2 is the tension. 1.2 is the tension. Result after tension is not there. After the string is cut, U minus mg. U is 2, mg is 0.8. So U minus mg 1.2 as m is 0.8, as the weight is 0.8, mass is 0.08. 0.08. 1.2 divided by 0.08. 15. Meters per square second. After the string is cut, it will move up with the acceleration of 15 meters per square second. After the string is cut, 15 meters per square second. Okay. Now it has to move a distance of 2 meters to reach the surface. It has to move a distance of 2 meters to reach the surface. So at the surface, what will be the volume velocity? Third part, V equals V square is equal to U square plus 2as. Now after the string is cut, upthrust force is greater, mg is lesser, so it's moving upward with the acceleration of 15 meters per square second. As soon as the string is cut, initial velocity is 0. As soon as the string is cut, initial velocity is 0. What will be the velocity at the top? V square. Initial velocity 0 to upward u minus mg over m 15. It has to move up 2 meters to reach the surface. So V square is equal to 60, where V is equal to root 60 meters per second. So object will have a velocity of root 60 when it reaches the surface. Now above the surface you have the free air. No upthrust force again. No liquid from there. No liquid from there. It will just move in the space and come to the highest point and it will drop down and it will drop down. So from there you have the, you can apply V square equal to U square plus 2as again, but it's in the free air. It's in the free air. When you consider the free air, you don't have a upthrust force that much of like liquid. So it's just a equation, it's just a question from motion under gravity. The starting velocity to move up is the root 60 value. So square will be 60 here. From the place where the object was tied by the string, string was cut. So U minus mg was the resultant force divided by m. You got the acceleration of 15 meters per square second. With that acceleration, object came 2 meters through the liquid and got a velocity of root 60 at the liquid surface. Above the liquid surface is the free air. in the free air, it's just a motion under the gravity. So at the highest point on the free air, at the highest point at h max, velocity is 0. Let's say v dash, it's 0. It's a motion under gravity. At the highest place, the velocity is 0. It started to move in the free air with the initial velocity of root 60, where square is 60. To a acceleration of gravity is minus 10 h max. H max, acceleration of gravity is minus 10. Why? Now we are in the free air. So 20 h max is equal to 60, where h max is equal to 3 meters. So object will move another 3 meters on the free air just before the drop down. After 3 meters, it will drop down to the water surface again. 3 meters. Okay. Now you will meet another question. At that question, they will tell you to consider the air as a liquid. If they have especially told you to consider air as a liquid, you can imagine about the upthrust created by the air when you consider air as a liquid. But in normal questions, our liquids, water, oil, kerosene, they are the liquids, and they are creating considerable upthrusts on the objects, and you have to consider that. But in the free air, you are neglecting the upthrust, a small upthrust that's being created by the outside air. Outside air is also a liquid, true. It's a kind of a liquid, and it will create a small upthrust. Normally, if nothing is especially told, we don't consider it. But if they told it especially to consider the outside air as a liquid, then there's a small upthrust we need to calculate. But in a normal question, they don't want it from us. So I did it normally. Okay, move to question number 39. Move to question number 39. After the question number 39, you will get the interval. Question number 39. A metal block of relative density 8 is suspended from a spring balance. Now there's a spring balance. In my mechanics lesson, when I'm doing the force and Newton laws, I have done the spring balance. Inside the spring balance, there's a spring. And the end of the spring is connected to a string type of a cable. And it comes to the attaching point. When you attach the object, what happens? Object has its weight mg. Object has its weight mg, and in the string balance, this cable-like thing attracts the connected point towards the string itself, T, and from the other side, it will attract the spring downwards, T. when the spring is attracted downward, the pointer will come down and it will read the T value. So remember, a free spring balance which is stationary, a free spring balance which is stationary is reading the tension. A free spring balance which is stationary is reading the tension. Okay, so this is the thing. And in this case, as the object is in equilibrium, object does not move, so T is equal to mg. So if the reading is if the reading is 20, that means the pointer shows 20, this tension is 20. So the other side of the tension is also 20. It balances the weight. So the 20 is equal to weight. Mass is 2 kilograms. Mass is 2 kilograms. Okay, let's brief it again. In my force and Newton laws lesson, I have taught you this thing. When you take a stationary spring balance, it reads the weight of the object, but this is how it happens. Inside the spring balance, you have a spring. That spring has a cable type of a bar at the end. This bar can be considered as a string, a cable type of a bar. It can be considered as a string, and we use the end of it to hang the weight. When the balance is set and the weight is attached, weight has the mg value downward. To balance it, the tension type of rod, the rod with that tension will attract the connected point towards the string, rod itself, T, upward. In the other side, tension is attracting the spring downward, T, and it is the reading. So if the reading is 20, all these T values are 20, from the equilibrium of the object, mg is also equal to 20, m is 2 kilograms. Now what happens? Now the same spring balance is present, but the object is fully inside the liquid. Spring is present, that rod type string is present, but the object is immersed inside the liquid. Now the object is immersed inside the liquid. Object is immersed inside the liquid. Weight mg, tension attracts the connected point towards the string itself. Weight mg, tension attracts the connected point towards the string itself, and as it's inside the liquid, upthrust is there. What is upthrust? The object has a top level and a bottom level, and there's a pressure difference due to the depth change on the top and the bottom, and this pressure difference creates different forces on the top surface and the bottom surface. So the resultant force remaining is upward, it's upthrust. So object has the upthrust, tension T upward, weight mg downward. So from the equilibrium, upthrust force plus tension is equal to mg. Okay, so from that method you can calculate the tension. Let's say here the tension is T dash. Upthrust is the volume of the object that is inside the liquid, and here it's the total volume. Density of the liquid G plus tension is also acting in the upward direction, attracting the connected point towards the string itself, T dash, is equal to weight. Weight can be written in density and volume, but you know the weight too, 20. Mass to weight 20. From here, weight is equal to 20. Volume of the liquid inside the water to calculate the upthrust. in question number 39. In question number 39, what is the volume of the object? For the object, I'll apply rho equals m over v. For the object, I'll apply rho equals m over v. I know the object is hanged from a spring balance on the air and it has the weight and the tension upward. Weight will balance the tension. Other side of the tension will pull the spring down and it becomes the reading. Reading 20, tension 20, weight 20, mass 2. Mass 2. And the density of the object is given. Relative density 8 multiplied by the density of water, the correct density is 8,000. Density of the object is 8,000. 8,000, mass 2, volume B. So volume is equal to 2 over 8,000. Volume is equal to 2 over 8,000. Volume is equal to 2 over 8,000. Okay. So the total volume related to the total mass is equal to 2 over 8,000. And it's the volume inside the liquid also, because the full volume is inside the liquid. To write the upthrust, you need the volume inside the liquid. Here it's the full volume, 2 over 8,000. Multiplied by the density of the liquid 1000 times G, 10. Upthrust plus new tension T dash is equal to weight 20 from the previous calculation. Okay? 1, 2, 3, 1, 2, 3. 20 divided by 8. 20 divided by 8. 2.5 plus T dash is 20. So the T dash becomes 17.5 newtons. T dash becomes 17.5 newtons. T dash becomes 17.5 newtons. Okay. So the tension that attracts the object upward is equal to 17.5 newtons. So the other side of the tension will attract the spring downward. It's equal to 17.5 newtons again. It's equal to 17.5 newtons again. It attracts the spring downward, 17.5. And the downward attraction of the spring becomes the reading. Remember that, huh? I have taught it. 17.5 reading. Downward attraction of the spring becomes the reading. It's equal to the upward attraction on the object. It's 17.5 now, because the earlier it was 20, but some part of it is covered by the upthrust. So it will become less, 17.5, and reading will become small. When you are doing in this school, if you have done this in the school, what is the special name for this reading? What is the special name for this reading? What is the special name for this reading? You have to remember it. When an object is fully inside, when an object is attached to a spring balance, and when the object is in air, the reading is the real weight. So it's the real weight. No problem. But when an object is attached to a spring balance and object is immersed inside the liquid, that's the upthrust acting on it, as we have done here. So upthrust plus tension is equal to weight. So the tension is not reading the weight. Tension is equal to U plus T. U plus T dash is equal to mg. So T dash is mg minus U. So the tension relate equal to weight minus upthrust here. That kind of a reading, the tension becomes the reading, and it is known as the apparent mass, apparent weight. Write it. Remember that word. Apparent weight. In a question, if they tell you apparent weight, they are giving mg minus u full value. When an object is inside the liquid while attached to a spring balance always read the tension. Normally tension is equal to weight in the normal layer. But here upthrust plus tension mg, upthrust mg minus upthrust plus tension mg here, tension mg minus upthrust. That mg minus upthrust full term, the tension, the reading is known as apparent weight. Apparent weight. Note down that. Note down that. Okay. Now it's time. Time is 9:07. 9:07. Okay. Let's meet at 9:20. Let's meet at 9:20. 9:22 is okay. 9:22. Okay. You can have a rest. Huh? Let's meet at 9:22. Thank you for the information, children. Thank you for the information. Now, I hope that you can hear me well. Okay, thank you very much. Okay, let's continue. Now, in question number 45, they ask us about a hot air balloon. Hot air balloon is a kind of a very large balloon. If you can remember the Windows wallpaper, the famous Windows wallpaper with a set of large balloons that the people are traveling on them. They are moving up on the sky using these hot air balloons. They are not like the normal balloons we use in birthday parties. In a small balloon we use in the birthday party, we seal the air inside it by tying it from the end. We seal the air inside the normal balloon. In a hot air balloon, this is what happens. It's a very large balloon. It's a very large balloon. A hot air balloon is a very large one. Nah? It's not sealed. It's not sealed. You have a hole here. And you have the basket where the people can stand. Where the people can stand. And here you have a burner. Here you have a burner. So, when the people, the operator, needs to move the balloon upwards, when the operator needs to move the hot air balloon upwards, this is what he do. He switch on the burner. He switch on the burner and heat the air. Heat the air inside. Listen carefully, yeah? Heat the air inside. In a hot air balloon, that's what happening. Using the burner, operator heats the air inside. It's not a sealed balloon, like a birthday balloon. It's open from the bottom. Using the burner, you can heat the air inside of it. You can Google search it. You can watch the diagrams. Okay? When you heat the air inside it, what will happen? Air will move away. Air will move away. When the air moves away, density inside decreases. Inside density of the air decreases. Inside density of the air decreases. When the inside density of the air is decreasing, the weight of the air, MAG, decreases. For the rubber balloon, it has a weight, capital Mg. It will be there, but the air inside will be reduced. You are heating the air inside and they will move away. So the inside air mass reduces. The rubber mass, the weight of the objects, it's same. It will remain. And remember, in a hot air balloon, it's very special. It's a very special rubber cover they use. It's very expensive. It will not change its volume, even the air inside it. Even the air inside it is moved away. By heating, still it will maintain a constant volume. It will maintain a constant volume. So this balloon is immersed. It is inside the liquid called outside air. This balloon is inside the liquid called outside air. Due to the outside air, there will be an upthrust acting on the balloon. There will be an upthrust acting on the balloon. Due to the outside air, there will be an upthrust acting on the balloon. That upthrust will move the balloon upwards. That's what's happening here. Okay? I'm giving you a small note after drawing this. Before drawing this is the situation. Hot air balloons are not the normal balloons you use to blow in birthday parties. They are not sealed. They have the basket at the bottom for the people to stand out, and a large balloon is there. And there's a hole from the bottom. From that hole, from a burner, you can heat the air inside the balloon. When you heat the air inside the balloon, inside air moves away and mass of the inside air decreases. And the density of the air decreases and the mass of the inside air decreases. The object mass and the weight, that remains same, but the total weight decreases due to the mass inside the balloon decreasing. But this special rubber cover does not change the volume, even though the inside air moves away. It remains same. So this volume of the balloon can be considered as a immersed volume inside the outside air. This balloon is immersed in the outside air. You can consider outside air as a liquid, and that liquid will create an upthrust on the balloon. That upthrust will move the balloon upwards when you are decreasing the inside weight by heating it. Okay, I'll give you a small note. Draw it first. Then I will give you a small note. Keep 2, 3. Okay, draw it in the left side, and in the right side we will finish the note, and you can continue the question also. Okay, draw it. Okay, write a small note about these hot air balloons. Write a small note. When we heat the inside air, when we heat the inside air, it moves away. When we heat the inside air, it moves away, reducing the density and weight of inside air. When we heat the inside air, it moves away, reducing the weight and the density of inside air. Reducing the weight and density of inside air. Reducing the weight and density of inside air. When we heat the air inside, it will move away, reducing the weight and density of inside air. But this special rubber cover will keep the same volume constant. But this special rubber cover will keep the same volume and outside air considering as a liquid, will create a good upthrust. And outside air considering as a liquid will create a good upthrust. To move the balloon upwards. 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 Okay. Now there's a small question. In the previous parts, we didn't consider the upthrust from the normal air. In previous cases, in the last question, when the mass was attached to a spring balance in the free air, it was just the tension and the weight we considered. We didn't consider the upthrust from the normal air in the previous questions. Why is that? Upthrust is equal to the volume inside the liquid, density of the liquid times G. When you consider a liquid like water, it has a density of 1000. So even for a smaller volume object, with a smaller volume, as the density is high, water will create a good upthrust. So inside water, always the upthrust is considered. But when you come to the free air, density is equal to 1.2, 1.3, very small value. So for small objects having a very small volume, when it is placed inside normal air, the upthrust is negligible. Consider a small object having 10 centimeter cubes of volume. Consider a small object having 10 centimeter cubes of volume. Volume is equal to 10 centimeter cubes. 10 into 10 to the power minus 6 volume. A small object attached to a string in air. Volume 10 centimeter cubes. 10 into 10 to the power 6 meter cubes. Density of the air 1.2. Acceleration of gravity 10. So what is the upthrust? 12 into 10 to the power minus 5 newtons. Neglected. So in normal cases, you don't need to worry about the upthrust created by the normal air, and we are not considering it. But here, take this practice. But here, this hot air balloon is having a volume of 1200 meter cubes. It's a very large hot air balloon. Normally, the water tank in your home on top of the roof is equal to 1 meter cube. So this balloon is 1200 times of the water tank that you have. It's a very large balloon. So what happened? Here, volume is very large. So even the density is small, still you will be a considerable value. So when you come to a very large volume object like a hot air balloon, you can't neglect the upthrust acting on it by the outside air, considering outside air as a liquid. So be experienced when you consider a very large volume object like a hot air balloon, you can't neglect the upthrust created by the liquid kind of nature of the outside air. But for a very small volume, it's a negligible answer. Keep it in your mind, and if you need, you can note down it and you can continue the work now. So it's a very large balloon and it will have a very large upthrust. Let's see the value of the upthrust. Upthrust is equal to the volume that is immersed inside the liquid, density of the liquid G. The full balloon is inside the air. It's immersed inside outside air. So the total volume will be the volume inside the liquid. The liquid is the outside air times G will be the upthrust. Let's see. Volume of the balloon 1200 meter cubes. 1200 times that of your water tank. 1200 meter cubes. Huh? 46, huh? 46. Let's come to 45. Let's come to 45. Let's do the 46 first. Okay. Upthrust acting on the balloon. Volume of the balloon, it's fully immersed inside air, 1200. And outside air density, 1.3 here, times 10. Let's see the upthrust. It's not a negligible value. As the volume is high, very high, 1002, multiplied by 1.3, multiplied by 10. 15,600 newtons. It's not a negligible value now, upthrust. Keep it. What is the weight of the balloon? Here they haven't mentioned the people inside the basket. So it's just the object weight, the rubber weight, especially this large rubber cover. It has a very large weight. It's about 400 kilograms. The rubber balloon, 400 kilograms. That means 4,000 newtons of weight. Upthrust 15,600, known weight of the rubber peoples are not considered. And weight of here 4,000 newtons. Okay. Then what is the mass of inside air? What is the weight of inside air? You know, in a hot air balloon, the bottom is not sealed. You keep a burner and heat the inside air. Inside air moves out and its density decreases and the weight of inside air decreases. Let's find the weight of inside air. Weight of air inside air is equal to volume of inside air multiplied by the density of inside air multiplied by G. Weight of inside air, mass of inside air into acceleration of gravity. Mass of inside air, inside volume into inside density. Inside volume is also 1200. Inside volume is also 1200. You have a small rubber cover moving, separating outside and inside, but you don't need to consider the volume of that small rubber cover. So the inside air is having a volume of 1200. Inside density, it is decreased due to the heating process. Inside density is 0.8 G10. So 8 times 1200, 9,600 newtons. So here I have calculated the weight of the inside air after the heating process. Most of the air moves out and the density and the weight decreases. Density is 0.8 multiplied by the 1200 full volume, neglected the rubber volume, multiplied by G. Now I know the inside air weight, and they have given me the weight of this rubber and the other objects, and upthrust is created from the outside air. Density acting on the 1200 volume calculated. So there's a mismatch. Still the upthrust is high. Upthrust is 15,600, but the air weight and the object weight is not that much. So upthrust is winning and it will move up. So what has happened? What's done? The operator has used a string. Operator has used a string to tie it to the ground. The tension will attract it downward more and more and will create the balance. Will create the balance. After attaching it to the ground by a string, upward force upthrust is balanced by weight of the inside air, weight of the rubber parts, plus tension of the string. Tension of the string attracts the connected point towards the string itself, and it's downward. Weight is downward, air weight, object weight downward, tension attached to the ground, it creates a force downward and will manage the upthrust. Upthrust is equal to 15,600, air weight 9,600, object weight 4,000. So what is the case now? The tension is equal to 2000 newtons. Tension is equal to 2000 newtons. Then, if the string is cut, find the acceleration that the balloon will move up. Now I will cut the string. Then what will happen? I'll apply F equals ma upward. After cutting the string, I will apply F equals ma upward. F is the resultant force, upthrust minus air weight, inside air weight, object weight is equal to inside air plus object mass times acceleration. I'm applying F equals ma upwards. When I'm applying F equals ma upwards, what is the upward resultant force? Upthrust minus air weight, inside air weight, object weight of the rubber is equal to total mass times acceleration. Total mass, inside air mass plus rubber mass. Upthrust 15,600 minus air weight. We calculated by the inside air density and the volume. 9,600. Rubber weight, rubber and the basket, 4,000 is equal to the resultant force equal to total mass times acceleration. No tension, string is cut. Total mass. If the inside air weight is 9,600, inside air is having a mass of 960. Inside air is having a mass of 960. And the rubber is having a mass of 400. They have neglected the mass of the operator. Okay, 960 plus 400 times A. 2000 is equal to 1360 times A. Acceleration is equal to 1.47 meters per square second. Acceleration is equal to 1.47 meters per square second. Okay. Now come to the 45th question and the 49th question. Here, our group work, the website management and the WhatsApp messages are done by my team, but most probably this phone, I'm keeping it too. So when you send me a message, I also see it. Sometimes I don't have the phone. Our team members do this work, but most probably I have the phone with me also, so I see them always. But now it's about another 60 days for the exam. So I'm working with the grade 13 students. So sometimes I will miss your messages, but definitely my team will inform me about the messages you sent. Then I will reply, or I will inform them the reply that you need, and you will get them. But I'm not that much involved now from this month, but you will get the team, our team will handle it, and you will get the replies. Okay, and the work will be done properly. Actually, they are doing that, but I always invigilate it. But here now I have 60 days for the A-level exam. Okay, remember that. Anyway, you will receive the replies. Okay, the next thing. This is a good news. And we are starting the paper class next month. It's a one thing. The other thing, this is also a very important message. After this time's A-level, after the A-levels here in this 2026 A-levels, in the month of September, I'm starting the revision. It's a full English medium revision. It's a very rare situation. In most of the cases, a English medium revision is not there. So in our case, we have this English medium revision. So, okay, in September, first week of September, I'm starting the English medium revision. So if you have doubts in the previous lessons, say force and Newton laws, or then the work, power and energy, for that separate part, you can join with the revision and you can cover them. Remember that. Okay. It is started on first month of September. physical revision is always there. Physical revision, physical English medium revision, it's always there. And this time, a special case, there's a 100% online revision also. There's a 100% online revision too. You can make the use of it. Okay. Now, let's discuss the question number 46. Let's discuss the question number 46. Forty-five. We did the 46th question. Question number 45. Now, if it is a very large balloon, I have shown you now, even the outside air density is small due to the large magnitude of the volume, upthrust increases and it's not negligible. In the hot air balloon case, outside air has to be considered as a liquid and you got the upthrust, 15,600 newtons, not negligible. Now you know that fact. When it comes to a small volume, a small object, the air density is creating a small upthrust, but it's negligible. But in a special case, when they give you the outside air density, even the volume of the object is small, if they are giving the outside air density, that hints that you have to consider the upthrust from the air. Normally, with a small object, they don't give you the outside air density. But if they have given you the outside air density as a fact, that means you have to use it to what? That means you have to consider the upthrust. Now you can't neglect it. Let's see. Okay, here in the 45th question, it's not a very big object. It is attached to a certain place using a string. It has its own weight and it's attached by a string. So the tension attracts the connected point towards the string itself, T. T is also there. Okay. So these are the two forces that we consider normally. But here, not like in normal questions, there's a special point. Why? They have given the density of outside air. They have given the density of outside air. The outside air density is equal to 1.2 kg per meter cube. So it hints that the outside air density is given. That hints that you have to consider the upthrust. It will not be a large value, you will see it. So normally if the outside air density is not given, we neglect that. Unless it's a very large object, we can neglect it. But here they give us the idea that we have to consider the upthrust from the outside air. Here, the mass of the object is equal to 180 divided by 1000 kilograms multiplied by 10. Weight is equal to 1.8 newtons. Mass is 180 grams divided by 1000 kilograms multiplied by G. 1.8 Newton is the weight. And the material density 800. Material density is 800. Rho equals M over V. Material density 800. Mass 0.18. If the weight comes as 1.8, mass 0.18, and the volume of the object 0.18 over 800 meter cubes from SI units. Now by the density and by the volume, by the density and by the mass of the object, we got the volume of the object. Now we know the volume of the object. So what is the upthrust acting on the object? Volume inside the liquid, upthrust, volume inside the liquid multiplied by the liquid density times G. Volume inside the liquid is the full volume of the object because this liquid is the outside air. Full object is inside the outside air. So the total volume of the object is the volume inside the liquid. Total volume 0.18 over 800 multiplied by density of the liquid. Density is the outside air, 1.2 times G10. So what is upthrust? You will get a very small value. 0.18 divided by 800 multiplied by 1.2 times 10. 0.0027 newtons. That's why. If it is not especially mentioned, that's why we are neglecting it. But here we can't neglect as they giving us the clue to consider it. It's a very small value. Okay. The tension attracts the object upward, equilibrium, plus the upthrust is also upward and the weight is downward. Tension of the string plus upthrust 0.0027 is equal to weight. Weight is equal to 1.8. So the tension is equal to 1.8 minus 0.0027. So the influence of the upthrust is very small. That's why we normally neglect it. We are considering it only in hot air balloons. When the balloon is large, as the volume factor large and the upthrust increases. But especially in this kind of a case, when they give us the outside air, then we can't leave it. We have to do this way. 1.8 minus 0.0027. 1.7973. Okay. Then move on to 49th question. Move on to 49th question. Question number 49. This is a object with a volume equal to 100, let's say V. This is the object A. It's attached to a string, comes over a pulley, and in the other side you have a object B. This part is inside a liquid container. This part is inside a liquid container. This part is inside the liquid container. Okay. So how to do this? First of all, it's good that they have told us the volume is same. The volume of the object A, 100 centimeter cubes. Volume of object B, 100 centimeter cubes. That's good. The both volumes are same. But densities are different, rho A and rho B. The density values are different. What are the density values? Object A having a density of 400 kilograms per meter cube, while B 1500. Okay. Now the objects A and B are attached by a string, and this string is moving over a pulley. So before moving to anything else, as the volume said to be equal and the densities are given, let's find the mass and the weight of each object, because that's essential. Mass and the weight of each object, that's essential. Let's find it. Okay. Mass of the first object A. Density is equal to mass over volume. So volume is equal, the mass is equal to density times volume. Mass is equal to density times volume. Mass is equal to density times volume. Mass, density times volume. Mass of A, density of A. Density of A, 400. Volume of A, 100 into 10 to the power minus 6. 1, 2, 3, 4. 0.04 kilograms. Mass of A. Mass of B, density of B multiplied by volume of B. Mass of B, density of B multiplied by volume of B. Okay, mass of B. Density of B multiplied by volume of B. Okay, density of B, what is the density of B? 1500. Density of B, 1500. And the volume of B is equal to 100 centimeter cubes. 1, 2, 3, 4. Mass of B, 0.15 kilograms. Individually applying rho equals m over v for both objects, now I know the masses of them. So the weight of A, mag, 0.4 newtons. I'm marking it here, 0.4 newtons. Weight of B, I'm marking it here. Weight of B, mbg, I'm marking it here. mbg, 1.5 newtons. 1.5 newtons. (1.5 newtons). Okay. Now, then here, when it is not specially told or the clue is not given, outside density is not given, don't consider the upthrust from the air. It's just the tension that attracts the connected point upwards. Tensions attracts the touched point with the pulley towards the string like this. Tensions attract the touched point with the pulley towards the string like this. Tensions attract the connected point of the object towards the string like this. I marked the tensions in the string and the weights were found and marked. Not going to consider the upthrust from the outside air, but from the liquid, it's this upthrust, it's essential to consider this upthrust. This upthrust U is essential. Upthrust acting on the object which is inside the liquid, UB. Let's find it, UB. Upthrust is equal to volume inside the liquid density times G. Upthrust is equal to volume of the liquid, density of the liquid, G. What is the volume of the liquid? That's inside the, what's the volume? Upthrust is equal to volume of the object inside the liquid. It's the total volume of B because it's fully inside the liquid, 100 cm3. Density 10 to the power 3. G is equal to 10. 1, 2, 3, 6, 6. Upthrust is equal to a 1 Newton value. 100 centimeter cube density converted to meter cubes, kg per meter cubes. Then density, the volume converted to meter cubes, density of the object B, sorry, not the object B, outside liquid density, water, 1000 G will give me the upthrust acting on the object. So now I know the values of the forces. Now what will happen? What will happen? Here, read the question. A moves downward. As they say, A will move downward. So the downward acceleration is A. Capital A moves down with a downward acceleration A. So it's a fact. So as they are saying that A is moving downward, the string will come this side and this one will move up. This one will move up. This one will move up. It's the situation. It's the situation. Okay. Applying F equals ma for A. Applying F equals ma for A. F is the resultant force. Weight 0.4 minus T. 0.04 times acceleration. Applying F equals ma for A. Applying F equals ma for A. 0.4 minus T is equal to 0.04 times A. Okay. Now, applying it downward because A is moving down as they say. Applying F equals ma for B upwards. What is the resultant force? B is moving upward as they say when A moves down. Tension plus upthrust. Tension plus upthrust minus weight of it will be the resultant force upward. Tension upward, upthrust upward minus weight will be the mass times acceleration. Tension I don't know. Upthrust 1 calculated. Upthrust 1. Tension. Upthrust is equal to 1 now. I know it. Weight 1.5. I know it. Minus 1.5. Mass 0.15 A. Mass 0.15 A. So these are the two equations. Applying F equals ma for A downward. 0.4 minus T is equal to 0.04 A. Applying F equals ma upward for the B. Tension plus upthrust minus 1.58. It will end up with T minus 0.5. Here, it end up with T minus 0.5 is equal to 0.15 A. Add in the equations, minus T and plus T will cancel up. Minus T and plus T will cancel up. 0.4 minus 0.5. Wait, what has happened? Density, the beta, volume 100 into 10 to the power 6. 1, 2, 3, 6. Upthrust 1 Newton. Weight of A 0.4. 0.4 minus T 0.04 A. And for the B, tension T plus upthrust 1 minus weight 1.5 is equal to 0.15 A. Adding them, here it gives a minus answer. Wait. Yesterday in the physical class we did it and we got the answer correctly. Let's see what has happened. Here the density is 4000. This is the problem. Here the density is 4000. For the object A, density is 4000. So mass of A, density 4000, you have another 10 here. Volume 100, okay. So the weight becomes 0.4 and the mass becomes 0.4 and the weight becomes 4. So not 0.4, it's 4. 4 minus T, not 0.4, 4. 4 minus T, mass 0.4 times A. And 4 minus T, 0.4 times A. And for this one, it's same. Now, first equation, 4 minus T, 0.4 times A, other one is same. So, here, 4 minus 0.5, 3.5 is equal to 0.55 A. And A will have a value of 3.5 divided by 0.55. 6.36. Now the answer is correct. Meters per square second. Meters per square second. Okay, now I got the answer. Okay. Now, as the final question, here in this side, from the 49th question, then we have the floating principle. We have the floating principle after the 49th question. Okay, we are doing that 50th question next week. But here I have to tell you a special thing. Can you do the 69th question now as the final question? Do the question number 69 as the final question today. It's a special point. Let's finish it. Then we'll come to the 50th question next week as the floating principle. Then we are finishing the hydrostatics next week. And we are doing the hair apparatus practical. And I will show you the, here we go to our webcam. And I will show how the practical is being done. If you haven't seen it in the school, I will show you the apparatus and I will show you how the practical is done. Let's do the practical. Okay, we have the facilities and you will see how the practical is done. Okay, hair apparatus. Then the floating principle questions. And we are finishing the hydrostatics next week and starting the fluid dynamics, final part of the mechanics next week. Okay. So today, for the final question, you have the homework up to 49th question. Finish all the questions before the 49th question, the in-between questions. From the 50th questions, we will do next week. But there's a separate star mark. Go to the 69th question now and finish it. Question number 69. Question number 69. Question number 69. This question is very special. It's giving us a special point. In question number 69, there's a balance like this. And in the balance, you have a spring inside. It's a spring balance. And the object is attached to it. And this object is inside a liquid. It's inside a liquid. This is the liquid. And here, the complete body is kept on another balance. Kept on another balance, and that balance is also having a reading. And this is also having a reading. Okay. A beaker containing water is placed on balanced B1. So this is the balanced B1. The beaker filled with water is kept on a balanced B1 as shown in the figure. The mass of the beaker together with the water is 5 kg. So this balance will definitely read 50 newtons because the mass of the water and the beaker is 5 kg. So definitely this balance will read 50 newtons from water and beaker. Water plus beaker. Water plus beaker, 50 newtons. An iron block of mass 1.5 kg. Iron block of mass 1.5 kg is there. Relative density 7.5. Density 7,500. iron. It's suspended from the balance B2. This is the balance B2, where the iron block is completely immersed in the water without touching the bottom of the beaker. Find the readings of the balance B1 and B2 respectively. Okay, let's do this. So what's happening here? Shall I find the weight of the iron block? For the iron block, density is equal to mass over volume. Mass is equal to density times volume. Mass of the iron block. Density of iron 7500. Relative density multiplied by 1000. Mass of iron 7500. Density of iron 7500. Weight is given. No need to worry. M is given. Let's find the volume of it. Volume of the iron block, mass over density. Volume of the iron block, mass over density. Mass is equal to 1.5. Mass is equal to 1.5. It's given. Mass of the iron block given. Divided by the density. 7500. And I will get the volume of the iron block. I will get the volume of the iron block. 1.5 divided by 7500. 2 into 10 to the power minus 4 meter cubes. Volume of the iron block 2 into 10 to the power minus 4 meter cubes. Okay. So the weight of the iron block 1.5 is the weight mass of the iron block. So the weight is 15 newtons. Weight is 15, and there's the upthrust acting on it. Upthrust on the iron block. Volume inside the liquid. Liquid density times G. When an object is inside the liquid, the upthrust force is starting. To calculate the upthrust force acting on the object, you have to consider the volume of the object inside the liquid. It's the full volume of the object. It's fully inside the liquid. What's it? 2 into 10 to the power minus 4. From the mass of the iron block and the weight of the iron block, we got the volume of the iron block, and the full volume is inside the liquid. So volume of the iron block is equal to the volume of the object which is inside the liquid. It's 2 into 10 to the power minus 4 multiplied by density. Outside density 1000 water multiplied by 10. So upthrust is equal to a 2 Newton value. Weight of the iron block 15 Newton. Upthrust 2 Newtons. Upthrust 2 Newtons. Okay. Then what will we do? Then let's pay our attention on the tension. Here the tension attracts the connected point towards the string itself, T. Tension attracts the connected point towards the string itself, T, and it will attract the spring downwards, T again. Tension will attract the connected point towards the string itself, upward, T, and spring downward, T. Okay. Object is in the balance. From the equilibrium, of the object, from the equilibrium of the object, upward tension T plus upthrust U is managed by the weight mg. T plus U is equal to mg. Upward forces, upthrust We found it. Tension attracts the connected point upward, T. T plus U is equal to weight mg. T plus upthrust 2, weight 50. So the tension is equal to 13 newtons. Now I know the tension. Now I know the tension of the string. It's equal to 13 newtons. Tension attracts the connected point upward. Here it's 13. And from the other side, it will attract the spring downward. 13. The force that attracts the spring downward inside the spring balance becomes the reading. So here, the reading is 13 newtons, 1.3 kilograms. Balance B2 will have a reading of 1.3 kilograms. Balance B2 will have a reading of 1.3 kilograms. Balance B2 will have a reading of 1.3 kilograms. Okay. What I did, they have given me the mass of the object plus the density of the object. So I found the volume of the object. I know it's fully immersed in the water. Use that volume times outside liquid density times G, found the upthrust. Understood tension plus U is managed by the weight of the object. From that point, I found the tension that is acting upward on the object. It's acting downward on the spring, and that becomes the reading. So the reading is equal to 13, 1.3 newtons. Got it. Now they ask us the reading of this B1 balance. What about the reading of the B1 balance? What about the reading of the balance B1? What about the reading of the balance B1? This is for B2. What about the reading of the balance B1? Think of a method. Now, for the balance B1, have you learned these theories? If you are in my class, I have taught you what is the theory for a table balance like this. What is the theory for a table balance like this? If you have a table balance, what happens? What becomes the reading of the table balance? The reading of the table balance is the downward press acting on that plate. Downward press acting on the plate. Always the reading of a table balance is the downward press acting on the plate of it. Okay. The downward press is equal to the water weight and the beaker weight, 50. But there's another special thing. From Newton's third law, there's always an opposite force created when one force is created. From Newton's third law, when one force is created, there's always an opposite force. So if the upthrust is 2 newtons, what do you mean by the upthrust? Upthrust is the force acting on the object by the liquid. Upthrust is the force acting on the object by the liquid. So from the liquid on the object, it's a 2 Newton upthrust. So from Newton's third law, the same amount of a force will act on the liquid downward, down thrust. Same amount of a force will act on the liquid downward, the down thrust. So the down thrust will push the plate. It has already 50 newtons from the weight of the beaker and the water, and upthrust is equal to 2 newtons. It's acting on the object from the liquid, from Newton's third law, from the object to the liquid. to the downward direction, there should be an equal force, down thrust. It's 2 newtons. So that too will also be felt by the plate here. So 52 newtons, 5.2 kg, 5.2 kg is the reading of the table balance. Is the reading of the table balance. Write this star mark as your final work. Write this star mark. Upthrust is the force. Upthrust is the force acting on the object by the liquid. Upthrust is the force acting on the object by the liquid. Upthrust is the force acting on the object by the liquid. From Newton's third law. From Newton's third law. From Newton's third law. From Newton's third law. An equal force will act downward. An equal force will act downward on the liquid by the object. From Newton's third law, an equal force downward will act on the liquid by the object. It is the down thrust. It is the down thrust. And it will increase the reading. And it will increase the reading by another 2 Newton value. And it will increase the reading by another 2 Newton value. It will increase the reading by another 2 Newton value. Okay, remember that point. Now, normally, when we are doing questions, it's always upthrust, upthrust, upthrust. Because in almost all the questions, what we consider is the object. Object is attached by a string and it has its own weight and the upthrust is acting on it. We are considering the object. So upthrust is the thing. But remember, in this kind of a point of view, it comes to the other side. When the upthrust is the force acting on the object, we always consider it to manage the object. But from the Newton's third law, don't forget that there's an equal and opposite force for each force. So if there's a force acting on the object called upthrust, there should be a force acting downwards on the liquid by the object. It's known as the down thrust. In this kind of a situation, you can feel it. When you keep a plate balance on the bottom of the plate, bottom of the container, you will feel it. Why? The water, the liquid, is pressed downward by an equal force called down thrust here. The plate balance will read the weight of the water and the beaker plus this down thrust. So it will increase by another 2 Newton value here. Yes, so these are the things. As I have explained last 20 minutes earlier, our next process is to understand the floating principle as our final subtopic. Then to do the hair apparatus practical, we will do it here and I will show you the real equipment and the practical. Then we are finishing it and we are moving to fluid dynamics next week. We are starting the fluid dynamics after finishing these parts. Okay, so finish the questions up to the 49th questions, the in-between questions, and we will start from 50 and we have done the special point in the 69th question. Okay then, good night.